Algebra 2 Cram, New York State, Algebra 2 Regents, Common Core, Basic Graphs of Inverse Trigonometric Functions. The domain of the inverse tangent of x, sometimes referred to as the arctan of x. This is concept number 17 in this Cram series. So to order this complete Cram session, inbox me at memedicine@gmail.com. Be sure to spread the words to your friends and classmates who also need to cram for Algebra 2. They too can inbox me at memedicine@gmail.com for pricing and ordering instructions. Now, the odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. If you attracted this cram session into your awareness, you are definitely above average and super genius. In all honesty, you already know this. It's just that there may be layers of virus code blocking your intellectual perfection. The Algebra 2 skills you want to develop are already perfectly developed. I'm just here to guide you in becoming aware of this by showing you how to think about Algebra 2 in a way that's going to get you optimal results, such as A's or perfect scores on your exams. Over a short period of time, these sessions will eliminate the virus code that blocks your awareness of your inner mathematical genius, okay? So you're expanding your level of awareness by cramming with me. And now you might be asking yourself, why do I have to pay for this entire session? Why do I have to make an investment? Well, purchasing this is psychological. The reasons for investing in this is psychological, and actually buying this benefits you more than it does me. Right now, you might be marginally interested in this topic, but when you pay for it, your level of interest evolves into commitment. The kind of commitment that says, I'm going to get my money's worth out of this. So commitment and accountability closes the gap between your intention of getting an A or a perfect test score and the actual result of manifesting your A or perfect test score, okay? So the concept of cramming often has a negative connotation, but what people are actually thinking of is hurrying, which is the result of fear, and consequently it can be destructive to your learning process. We're not hurrying, we're cramming. There's difference. Hurrying is jam-packing tons of unorganized information into your mental, spiritual DNA over a very tiny amount of elapsed time. Cramming, on the other hand, is taking a quantum leap in your understanding in an organized way that seems to take place in an instant. All right, so that was a mouthful. Now let's delve into the concept of the domain of the inverse tangent of x. Basic graphs of inverse trigonometric functions. And remember that inverse trigonometric functions emanate from the original basic trigonometric functions, such as sine, cosine, tangent, cosecant, secant, and cotangent. Okay? All right, so let's delve into this. Domain of the tangent of x, or the inverse tangent of x, rather. And when I say domain, the domain of the function is a set of all possible values of the independent variable, usually x, or the variable along the horizontal axis in a coordinate plane. Okay? Now, the secret to progressing through this concept beautifully is getting things in order. So before we actually delve into the concept of the domain of the inverse tangent of x, what I want to do is organize the original function, the originating function in your mind, which is going to basically be the tangent of x. Okay? Or here, it's going to be theta. All right, so here you see that you have an XY Cartesian coordinate plane and an acute angle
in standard position. When I say standard position, these are the features of an acute angle in standard position. The vertex of the angle is located at the origin. The initial side ray with its extent at its x-coordinate is located on the positive x-axis, and the terminal side ray is located within quadrant 1 to the extent of the y-coordinate, okay? And the terminal side ray, if you resolve it into its x and y coordinate, what you have is the formation of a right triangle. All right? And this is what we use to teach the concept of the basic trigonometric functions. So what you also are going to notice is that the extent of the adjacent side goes to the extent of the x-axis, which is positive in quadrants 1 and 4, negative in quadrants 2 and 3. And the opposite side, or the sine of the angle, when you form your right triangle, goes to the extent of the y-coordinate, which can be positive in quadrants 1 and 2, but negative in quadrants 1 and 3. Okay? And then you have the hypotenuse, or the terminal side ray, or the longest side of the triangle. And what I want you to notice is that this quantity is always going to be positive, because unlike the coordinates, it's not a location in the Cartesian coordinate plane, rather it's a measurement of magnitude of the length of the longest side of the triangle, or the hypotenuse, or the terminal side ray. And the equation to calculate this feature is always going to be squared. So even if you input negative coordinates, the output will always be positive because you're using something, or you're going to be using the distance formula. Okay? And when you have all these features put together and you calculate the inverse trigonometric functions for such an angle in standard position, these angles are referred to as principal angles or reference angles. Let me demonstrate what I mean by that. Theta reference, excuse the sirens in the background, kind of wakes you up a little bit. And what I mean by this is that your calculator, when calculating the inverse functions, it's always going to be calculating the values for primary angles or acute reference angles in quadrant 1. And recall that all acute angles are bound by the quadrantal angles 0 degrees and 90 degrees. Okay, so if you want the equivalent in quadrants 2, 3, and 4, you're going to have to do a little bit of work. But don't worry, I'm going to show you how to do that. It's not difficult. It's just that you have to have an organization system in your mind, okay? So with all this, the tangent of theta, because that's where we originate our inverse tangent function from, this is our angle theta. And the reason why I included x is because a lot of people aren't familiar with the Greek angle variable naming system. Usually they see the tangent of x, but because we don't want to double up on variables, because the inverse tangent of x actually represents the function whose okay, this is how you would say it. The answer to this would be the set of all angles whose tangent is x. Okay, but don't worry about this now. We're going to get into it in a little bit. Okay, so the tangent of this angle theta, and this, disregard this x because this x is different and so is this x. So temporarily just disregard this. I call this theta originally because I don't want to double up on variables and confuse you more than I probably already am, okay? So the tangent of theta is equivalent to y, or the opposite side, or the sine, divided by the bottom side or initial side of the angle, or adjacent side or cosine of the angle, okay? And recall, these are coordinate locations that can be negative or positive, making the tangent negative or positive, okay? All right, but we're not here for that. We're actually here for the inverse tangent of function. And the inverse tangent function is the inverse, obviously, of the function tangent of x, or tangent of theta. And it can be gotten by interchanging the respective independent and dependent variables of the tangent of theta, or interchanging the entire domain and range of the tangent of theta will yield the function, the inverse tangent of the x, or theta, okay? So basically, you're just switching all the x and y values of tangent to get the inverse tangent function. And so another alternative name for the inverse tangent function is the arctangent function, arc with a capital A, and we'll see why this is important in a few. When the A is capitalized, again, this is defined as the set of all angles, because all inverse trigonometric function yield angle answers, usually in degrees, whose tangent has a value of x, okay? All right. So let's say the x were 1. Then the principal angle, or the reference angle here, would be 45 degrees, okay? So that's an example. And when the A is capitalized, it has a different meaning than when it's lowercase. But don't worry, I'm going to organize all this for you really, really soon, all right? So let's get back to our pre-example. We're interested in the inverse tangent of the angle. So we're going to take the inverse tangent of both sides of this expression. So whatever we do to the left-hand side, we're also going to do to the right-hand side. And when we take the inverse tangent of theta, which has the numerical value of y over x, equals the tangent of theta, we're going to yield the inverse tangent of the inverse tangent of y over x, which is the numerical value of the tangent, is equivalent to the inverse tangent of theta, okay? And taking the inverse tangent of the tangent basically just cancels out and undoes the function, leaving you with the value of the angle. So the inverse tangent of y over x is going to equal theta, or let's say you're referring to this angle as x, you would call it x, okay? All right. So now for the original intent. What is the domain? And when I say domain, again, I mean the domain of the function is the set of all possible independent variables, usually x, of the function y equals the inverse tangent of x, sometimes called the arctan of x. And I have the a here lowercase for a specific reason. So definitely press pause if you need to and take a moment to think. And if you don't know what the heck is going on, listen to me while I explain the conventions for calculating inverse functions in the various quadrants. Or if you know how to do that already, press pause and draw out your answer in the form of a properly scaled graph to demonstrate what a visual of the domain of the inverse tangent of x would look like, okay? All right, so for those of you who need to press pause, go ahead. And for those of you who are like, huh? What I want you to do is just chillax and listen to me as I explain the quadrant convention for reference angles, okay? So let's say you were to do a vertical flip about the y-axis in your reference angle, which will assign a value of 40 degrees, was flipped over into quadrant 2. But let's say your question stem wants to know not the principal angle or the reference angle in quadrant 1. It wants to know the equivalent in quadrant 2. And you're actually interested in this obtuse angle rather than the acute reference angle. What you would have to do is subtract theta reference, which is this. I just don't feel like writing out REF each time, from the extent of quadrant 2, and the extent of quadrant 2 is 180 degrees, okay? So 180 degrees minus our example theta reference, which is we called 40 degrees, we assigned a value of 40 degrees, is going to be 140 degrees. So 140 degrees in quadrant 2 has the same numerical value for tangent as 40 degrees in quadrant 1. Now we have to check for the sign convention. Well, since the y coordinate is positive, the numerator is positive, but the x coordinate is negative, so the numerator is negative. So it would be the negative numerical value of the tangent of 40 degrees, okay? Hopefully that didn't confuse you too much. Now let's say we did a diagonal flip about the origin, and theta reference ended up in quadrant 2. We would have to basically add theta reference to the extent of quadrant 2. And I said quadrant 2, I actually meant it ended up in quadrant 3. So you would have to add theta reference to the extent of quadrant 3. Well, the extent of quadrant 2, I'm sorry, which is the initial beginning of quadrant 3. And so what you're going to do is basically add 40 degrees to 180 degrees, which is the extent of quadrant 2, to get 220 degrees. So 220 degrees in quadrant 3 has the same tangent value as 40 degrees, our theta reference, in quadrant 1. And when we check our sign, check for the sign, we see that y has a negative value, the y coordinate has a negative value in quadrant 3, and it has a negative value for the x coordinate in quadrant 3 also, therefore making the overall tangent positive. So theta reference in quadrant 1 and the equivalent in quadrant 3 has the same tangent value. Okay, now let's check for quadrant 4. Let's say you did a horizontal flip about the x-axis, and your theta, when I say theta, I mean theta reference, ends up over here. What you're actually interested, though, in is this obtuse angle and not the acute theta reference. And basically, what you would have to do is subtract theta reference, the REF not indicated, but just picture it, imagine it in your mind's eye, from the extent of quadrant 4. Notice when the quadrant is positive, you're subtracting theta. But when the quadrant is even, you're basically subtracting theta. But when the quadrant is positive, you're adding the value of theta. Okay? So you would subtract theta reference from the extent of quadrant 4, and that's going to be 360 degrees minus 40 degrees to yield 320 degrees. Now when you check for the sign of the tangent, the y-coordinate is negative, the x-coordinate is positive, so the numerical value is the same as theta reference, but the sign is negative or opposite theta reference for quadrant 4, okay? Regarding the tangent function. All right. Yeah, so I think that's pretty much it for the pre-example. So hopefully by now, you either press pause and arrived at a pictographic answer, or you just are waiting to see how to calculate or how to demonstrate the domain. Okay, so what I'm going to need you to understand is that the originating function y equals tangent of x is not a one-to-one function. Rather, it's a one-to-many relation. That's kind of why I demonstrated the whole reference angle phenomenon here, because we see that 40 degrees would have the same tangent as 220 degrees, and 140 degrees would have the same tangent as 320 degrees. Okay, so this is like a one-to-many relation. And this is going to be problematic. Here we have our tangent function, the function that generates the inverse tangent function. And it's a legit function because it passed the vertical line test, meaning that whenever you draw a vertical line through the function, it's only going to intersect the function at one point. So although this function looks a little complicated because it has a lot of vertical asymptotes, it still passed the vertical line test, so it's a legit function. However, it's not a one-to-one function. As I previously mentioned, it's a one-to-many function. And the way you determine that is via the horizontal line test. When you draw a horizontal line through this function, it intersects at many points, okay? And that's problematic for making a legit function out of the inverse tangent of x, because earlier I told you in order to generate the inverse tangent of x, you basically switch the range and domain of the tangent, or all the x and y values. So if you're going to be interchanging these values here, when you yield the inverse tangent function, it's not going to be a legit function, because let's say you were to flip this tangent function, I don't know, like I think it would be like 180 or 90 degrees, and that horizontal line here became a vertical line, you would see that it's not a legit function, okay? So what we're going to have to do to make this a legit function is restrict the domain so that the vertical line drawn for the through the inverse tangent function won't touch the curve at many places. It'll only intersect at one point, okay? Because this right here yields an arctangent function with a capital A rather than a lowercase a. And that's not what we want. So what we're going to do now is just restrict the domain. And in the world of trigonometry, restriction can be done arbitrarily, but the region used for the inverse tangent of x is usually going to be negative pi over 2 to pi over 2, okay? And if you compare the graph of the arctan to the tangent, you can see that one can be gotten from the other by interchanging the horizontal and vertical axes, which is another way of saying switching all the x and y values, okay? And the simplest way to go about doing this is just going to be by reflecting the function, the restricted function of y equals the tangent of x about the line y equals x. Here goes our line, y equals x. So to generate our restricted arctangent or inverse tangent function, we're going to just flip the tangent function about the line y equals x. And now is where I get to explain to you the lowercase a. The lowercase a means that the domain has been restricted so that this is no longer defined as the set of angles whose tangent has a value of x. Rather, it's defined as the angle between negative pi over 2 and pi over 2 whose angle has a value of x. And just in case you're wondering, pi over 2 is negative 90 degrees, and negative pi over 2 is negative 90 degrees, and pi over 2 is 90 degrees. The conversion factor for radians, which always has a variable of pi, and degrees is going to be 180 degrees over pi. So pi radians has a value of 180 degrees, and this is a conversion factor to go from radians to degrees, okay? All right, so let's get to flipping. So when we flip the function about the line y equals x, you get this pretty little bad boy right here, which is y equals the inverse tangent of x, but the domain is restricted. This is an alternate name for the inverse tangent of x. And again, this new function is defined as the one angle between negative pi over 2 and pi over 2 radians, or between 90 and negative 90 degrees, whose tangent has a value of x. It's now a one-to-one function, and that's really good. And first of all, it's a legit function because it's going to pass the vertical line test. We see here that, the line only intersects at one space. But let's say we didn't restrict it, and you had all this stuff like so. That vertical line would be intersecting the function at many places, and therefore this would not be an even legit function that we could discuss. But that's not what happened here. We restricted our domain, and we have this pretty inverse tangent function, or arctangent function, you can also call it, okay? And again, if you want to measure the y coordinates in degrees, you can simply use the conversion factor between radians and degrees to convert from, let's say, negative 360 degrees to positive 360 degrees. But we don't do that here because we use pi because it's a more convenient unit. It's more condensed. If you had all the degrees between negative 360 and 360, there would be tons of hash marks and your graph would be very busy. That's not cute. So we're not going to do that, okay? And here we can answer our original question. The domain of the inverse tangent function, or the arctangent function, is going to be all real numbers, okay? And this isn't a question, but the range is from negative pi over 2 to pi over 2. Exclusive, meaning that it's going to continue forever in the negative infinity direction and positive infinity direction, never touching pi over 2 or never touching negative pi over 2, okay? Which is, you can also call negative 90 degrees and positive 90 degrees. And we're going to neaten things up a bit because this might be confusing you. So again, here goes a representation of the y equals the inverse tangent of x, with the domain going on forever in the negative infinity direction and positive infinity direction. So the domain is going to be all real numbers. And just in case you don't know what a real number is, real numbers include integers, such as the counting numbers along the number line, like 0. You could have something over here, -2, so that integers can be negative and positive, okay? Real numbers also include rational numbers. When I say rational, I mean a number that can be expressed as a fraction a over b, where b in the denominator is not equal to 0, but can implicitly be 1. So some examples are 2 over 1. Or that's 3. Or it can be 2 over 3 also. And the neat thing about rational numbers is that when you express them, when you convert the fractions to decimals, they terminate. So if you were to convert 2 over 1 into a decimal number, it would be 2.0, or they repeat. Or if you were to express 2 over 3 as a decimal, it would be 0.66, with the 6 repeating forever, okay? But an irrational number can't be expressed as a fraction, because when you try to express it as a decimal number, it's not going to terminate or repeat. So an example of this would be the square root of 2, which can implicitly have a denominator of 1. You're never going to see this, because when you do try to express the square root of 2 as a number, you're going to get something, as a decimal number, you're going to get something like 1.4142. And I'm not going to write the rest because it's taking up, well, I can't write the rest because it goes on forever. Yeah, so 1, 3, 5, 6. Those are all the digits that I remember. But this is going to go on and on and on forever. It's never going to terminate. So real numbers also include these numbers, irrational numbers, okay? So again, the domain of the inverse tangent of x is all real numbers. I know that was a journey, but once you get all that stuff organized in that beautiful mind of yours, you're just going to excel. Okay? And the intellectual comprehension of this material is not difficult. And after this short amount of time it's going to take to complete this entire cram session, if you purchase the entire thing, you will be prepared to answer a battery of questions about Algebra 2 concepts. Prior to the session, or throughout the demonstration, you may have been saying to yourself, wait, I know this. With regard to the various topics that we just discussed. But knowing and doing are worlds apart. So what this cram session has done is it closed the gap between you knowing and actually doing. When I say doing, drawing out the graph, knowing what a real number is, knowing the quadrant rules for calculating inverse functions. So yeah, we just closed the gap between knowing and doing, and thanks for tuning in. Thank you for your time.